when we are applying the integral test on a series contained of positive terms, here's some pro tips on applying that. Okay, so you want to make sure, first of all, that the conditions are met, and there are 3 of them. The first thing you need to check, are your terms actually positive? So, of course, you have replaced your series with a function. Hopefully that function's continuous. That's going to be one of our conditions anyway. But the first thing you check is it positive? You might think of what the graph looks like that e to the negative x was easy enough to conclude that it was positive, or you might take it piece by piece. If it's a fraction, is the top negative while the bottom is positive, stuff like that, right? And then you want to check to make sure your function is continuous. Continuity, most functions that we're aware of are continuous on their domains. You just got to make sure that your domain is in check, that it's got to be continuous greater than or equal to 1, and you're in business. Most of the time, you're just going to have some vertical asymptotes, and those vertical asymptotes probably exist outside of your domain. If they don't, then you just kind of have to take that into consideration. Oh, okay, we're going to start at 2 instead of starting at 1. All right, and then the last thing, decreasing. How do we check whether or not our function's decreasing? We look at its derivative and make sure that our derivative, first derivative, is negative as long as x is greater than or equal to 1. All right, so then after those conditions are met, then you look at the improper integral, and you're able to conclude that the improper integral and your series both do the same thing. However, you do not know, just because your improper integral converges to some number, like 1, that doesn't mean that your series also converges to 1. We'll see that towards the end of the lesson. Okay, so just because our improper integral converges to L, whatever this L is, it's a finite number, doesn't necessarily mean that our series converges to that same number, 2. Okay. So it's often harder to find out what the series actually converges to, like what the whole thing adds up to. And mostly what we deal with is, does it converge? All right, well, we're in step in the right direction. And then it's definitely tougher unless you've got something like a geometric series to be able to see what the series actually adds up to. So let's take a look at another example or two, shall we? Example 2, determine whether the series sum from n equals 1 to infinity of 1 over n squared plus 1 converges or diverges. Well, it looks like this one's a pretty good candidate for the integral test. I'm looking at that thing right now. It almost looks like arctangent, right? Think of that as 1 over x squared plus 1. Arctangent, well, it's not always positive. However, it is positive where we need it to be positive, as we'll see here. Notability, you have to restart too? Fantastic. All right, let's scroll down here. 4, example. Example the 2. I think it's 2. It's 2. All right, so our series from n equals 1 to infinity of 1 over n squared plus 1, we are going to consider the function f of x is equal to 1 over x squared plus 1. Okay, so let's meet our conditions if we're going to apply the integral test to this one. The first one is the thing positive? Okay, so I just now realized that I was thinking of the antiderivative. This is arctangent. This thing is always positive, right? The reason why it's always positive, it is rational function. Not that really matters here. I've got on the bottom x squared plus 1. X squared is always positive. We add 1 more to it. It's always positive. The whole thing's always positive. Right? Okay. We only need it to be positive for x is greater than or equal to 1. Check. We're good to go on the positivity part. Number 2, is it continuous? So for continuity, continuous, this is a rational function. Rational function is continuous on its domain. In its domain, it just happens to be all real numbers. So x squared, we're taking some sort of number, we're squaring, add 1 to it, it's never going to be 0. That denominator is always a positive number, as we pointed out. Whoop, where are you going? Okay, so f of x is a rational function okay, there we go, which is continuous on its domain so f of x is continuous everywhere, right? I think I need a verb in there. Is continuous everywhere. All right, we're good to go on that one. Check. Second check mark. Let's hope. Keep your fingers crossed that it's decreasing. All right, number 3, decreasing. Let's take its derivative. So before I do that, I'm going to rewrite it as x squared plus 1 to the negative 1 power. F prime of x is equal to negative x squared plus 1 to the negative 2 power. It is a composite function, so use your chain rule times 2x. Rewrite that thing as a negative 2x over x squared plus 1 squared. Okay, as we talked about before, bottom there is always positive. All right, and then the only thing that really matters is the top. Well, remember that we're sticking in numbers for x that are greater than or equal to 1, and we're multiplying that by a negative 2. So no matter what, this is going to be less than 0 for x greater than or even equal to 1. Yep, there we go. So what does that mean? That means our function must be decreasing. Since f prime of x is less than 0 for x is greater than or equal to 1, f of x is decreasing on x is greater than or equal to 1. There's our third check mark. Wow, that's a lot of work just to make sure you can actually perform this test. Okay, so now let's actually perform it. We want to take the improper integral from 1 to infinity of 1 over x squared plus 1 dx. Turn that into a limit as b goes to infinity of the definite integral from 1 to something, b, of 1 over x squared plus 1. What's that thing? It's supposed to be this thing, dx. Okay, again, I want to recognize that antiderivative as the arctangent of x. Arctan x from 1 to b. Throw your stuff in there. Limit as b goes to infinity of the arctangent of b minus the arctangent of 1. Let's consider the graph. Maybe you know these values off the top of your head. That's fine. If you don't, you can think of what the graph looks like. Remember, it's just a reflection of, we're going to go with pink? Okay. It's a reflection of the tangent graph, at least from negative pi over 2 to pi over 2, across the line y equals x, because it's the inverse, right? So it should look like this. Okay, and our numbers up here, this is a pi over 2, and this one is a negative pi over 2. For its horizontal asymptotes. Okay, all right, we're ready to take the limit then. So as b goes to infinity, arctangent of b, this is shooting off towards the right over here. Our arctangent's getting closer and closer to pi over 2. All right, and then there's nothing to actually stick into the arctangent of 1. So it's the tangent of some angle is equal to 1. That is pi over 4. What equals minus pi over 4. Half a pi minus a fourth of pi is equal to pi over 4. What does that mean? That means it converges. Check. All right. So our integral converges. This means that our original series must also converge. Does it converge to pi over 4? Have no idea. It does converge though. Okay. So I want to actually make sure that I write up all of those conditions that are met and then draw the proper conclusion. Since f of x equaling 1 over x squared plus 1 is positive, continuous and decreasing for x is greater than or equal to 1, and the improper integral from 1 to infinity of 1 over x squared plus 1 dx converges, then the summation from n equals 1 to infinity of 1 over n squared plus 1 also converges by the integral test. Dun, 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 dun. There you go. All right, maybe go ahead and stop this video, give you time to go get yourself a drink of water or something like that. Lemonade. And then we'll take a look at another example before we start P-Series.